Yeah, excellent.
Good?
Yeah.
Okie dokie. I think we are ready to kick this off. Thank you everybody for coming. And I'm really happy to host our speaker for the CS Colloquium / USC Center for AI and Society seminar today. And again, our speaker is Andrew Zolli, who is the Chief Impact Officer at Planet. And Andrew also leads the Global Impact Initiative on Planet and makes sure that Planet's data and its services basically achieve the highest impact that they can have in order to help humanitarian and conservation and sustainable development outcomes. Andrew is also an accomplished author. He has a best-selling book, Resilience, Why Things Bounce Back. And today he's here to share with us some of the amazing work that Planet has been leading using satellite data to inform humanitarian sustainability and conservation efforts. And I'm super excited to hear.
Thank you so much.
Thank you, Andrew.
Hello, everyone. It's so good to be here with you. What time is it? Is it 4 o'clock? The peak learning hour of the day, as you all know. This is the asymptotic minima between the time when you last ate and like all the blood has rushed out of your brain here at this hour of the day. So I'm really excited to come and spend some time with you, and I really appreciate all of you showing up. Normally I'd have a clicker and I'd be walking around, but because I forgot my clicker for some reason, I have to stand a little bit next to my laptop. So thank you very much for the introduction. It's wonderful to be here with you, and it's particularly wonderful as we have been slowly figuring out what it means to be an advisor to CAIS and to the whole effort. And as we continue in this learning journey together, it's really great to expose you to a little bit of the work that we're doing on the applied side. As was mentioned, I'm Andrew Zolli. I'm the Chief Impact Officer of an organization called Planet. I'll tell you much more about the work that we do at the beginning, but maybe just a very quick slide. Oh, wait, can you put the slides up? I realize the slides are not up. Oh, it would help if I plugged them in. So hold on, let's try this one more time. Otherwise, I will give this colloquium as interpretive dance, and it cannot be unseen. I will just tell you in advance. So just a very quick thing about just sort of maybe 3 or 4 bullet points to give you some sense of my kind of my perspective on the world. So today, I work to ensure the humanitarian, climate, sustainable development, and social impact initiatives of an organization called Planet. I'll tell you a lot more about them, but we're probably best known for having built and deployed the largest constellation of Earth-observing satellites in history, and we use very sophisticated tools of machine learning in service to frontline institutions working in everything from public health to climate to poverty alleviation and many other fields to help organizations grow and thrive and prosper and deliver their services more effectively. But just a few other things about me. I've also served as one of the explorers in residence at the National Geographic Society. I'm part of their Big and Tall program where they fit fat men into submarines and send them to the bottom of the ocean. You've not heard of that. Okay, just assume that I do a great deal of work on systemic resilience, on systemic and social resilience in particular, and have worked with frontline social services institutions. And one of the things that was most exciting to me about the work of this organization in particular was the way in which you cross those spaces. You know, the one thing, if there's like a lesson that so I'm not going to give you a technical talk. I could give you a technical talk. I'm just going to show you stuff and show you examples of what's happening in the world and talk a little bit about the kind of broader forces that are happening outside of academia. But if there's one observation I could tell you is that the world is rate limited by a certain kind of person. By which I mean the presence or absence of what we in the industry call T-shaped people. People who have broad perspective, and some of the grad students and I were just talking about this. People who have broad horizontal perspective, have a systems view, and have an understanding of systems change, and a narrow technical speciality that allows them to plug into complex adaptive systems and to improve them. And that is very hard to find. It's particularly hard because over the long arc of your careers, those of you who are students, whether you're graduates or undergraduate students, you will not just be T-shaped people, but eventually will then be pie-shaped people. And then you'll be whatever it looks like when you have a table with 3 legs and 4 legs, because the disciplines that we're all going to need require us to, we're going to have to add them to as we go. So, you know, I'm working in an organization today that was conceptually impossible to exist. Like the core fundamental technologies that I'll share with you didn't exist at all when I entered the workforce. And so we're in this really interesting space where we need folks who operate at these different dimensions. So a few other things about me. I spend a lot of my time working on issues of systemic and social resilience, looking at the heuristics of complex adaptive systems and resilience in systems and in communities and in people, and what are the things that rhyme across those domains. And I also spent a chunk of my time running an institution called the Garrison Institute that brings together people working in frontline issues of trauma, PTSD, and social environmental change, and a whole bunch of other things, and the great contemplative practices, and looking at the intersections of those spaces. So my work goes from the meditation mat to satellites on orbit. I am a weirdo. And what I will tell you is that you should all be weirdos too. And the fact that of this institution, CAIS, is itself a kind of a weirdo institution that covers these different spaces, is the highest compliment that I can pay you, because it's purely optimized for the kinds of problems that we're going to have to solve, even if you haven't solved them yet. That's really exciting. Okay, so I'm going to give you a talk. I'm going to show you a lot of pretty pictures of things we can do with remote sensing and AI. Hopefully you will find some of them inspiring. And I'll give you some examples of things that are yet to come, that are still in the little previews of things to come, perhaps at the end. But before we do this, I'm going to do a little exercise with you, if you don't mind, okay? I'm going to show you 2 images on a screen, okay? They'll all be the same. They're going to flicker back and forth like this. Took me a while to learn how to do that. None of you are appreciating on me from my ability to make that popping sound, okay? And I promise you there is one and only one difference between them, okay? When you see the change, I would like you in a non-competitive way to raise your hand, not to block the view of the people around you, but simply to indicate to me that you have registered where the change is, okay? That's it. This is a change detection exercise. Are you ready? 3, 2, 1. If it's helpful, I will hum the Jeopardy theme song. None of you know that joke. Some of us know that joke. But. Okay, we got 1 and 2, both women, not surprising. Can we get to 3? 3, okay. Now, how many people here saw no difference between those 2 images? I'd like you to raise your hands. Honestly? I'd like you to meet the honest cohort here. I don't know what those other 3 people were looking at. Those images are exactly the same. No, they were not, actually. Okay. For those of you who didn't see it, and that is about 90% of you who didn't see it, I would like you to pay attention to this part of the image, and I'd like you to watch as the thing that holds airplanes in the sky disappeared in front of your eyeballs over and over and over again, okay? And those of you who did, and there's only 3 of you who did, don't feel that good about yourself because it took you 30 repeat exposures. And the voice of God, because I have the microphone, telling you there was a change for you to notice it, okay? So, why did we miss it? Students, faculty, anyone here, why didn't we see this change? I'd like to know. Give me an hypothesis. Too much information, okay? It's a complicated image. What's else true? Okay, really interestingly, let me modify what you said. Human beings are exceptionally good at detecting change where we expect it to occur, where we have been trained to expect it to occur. What else is true? Let me just ask you this. How many people here, by show of hands, started by looking at the uniforms of the soldiers? How many people here, first or second choice, looked at the tail of the aircraft? Now, see how many hands are going up on these things? None of you communicated with each other. You all followed very similar search strategies, right? The reason is human beings are exquisitely sensitive to changes that happen in the social domain. We're not used to disappearing aircraft engines. And, you know, now, having this in mind, every time I go down the jetway to get on the plane, I check, is there an actual engine on the plane, okay? So we have this fundamental problem. And this fundamental problem, I think, is really well articulated by a colleague of ours, Stuart Brand, who said in our society, the fast-moving trends, the things that get the news, they get all the attention. The slow-moving changes, the changes that are happening in the background, tend to not get enough attention. And what happens is that because human beings are very good, among other things, like we're very bad at detecting change that moves like this. Okay? We're very good at detecting change that moves like this, about 1 meter a second, something like that. We're also really terrible at detecting change that moves like this, or that moves in an area or domain where we're not paying attention. And this challenge, this is a really hardcore challenge, because what happens is change accumulates in those spaces, okay, until it reaches critical thresholds and tipping points and then becomes uncontrollable change. So let me play a little game with you, okay? Maybe you've heard of it. I'm going to show you 2 images on the screen. They're going to flicker back and forth. Do you remember all this from 15 seconds ago? Okay. When you see the change between the 2 images, I'd like you to pay attention. This is what humanity does to the Earth. Here's the first one. Here's the second one. Now, see if you can notice. It's subtle, but humanity does have an impact on the planet, okay? Humanity fundamentally terraforms and transforms the Earth for our own purposes, right? Primarily for agriculture, habitat, and resource extraction. Those are the 3 things we like to do a lot. And we also like to eat. Right, so agriculture and fishing and all the rest of it, okay? These kinds of changes, we don't see them every day. You don't see them on a Tuesday here at USC in this lovely conference room. But they're happening right now, and they cause cascading effects. And those cascading effects are out of the realm of our normal cognition, and so they are difficult to solve for, in the same way that dealing with veterans who are dealing with PTSD and substance abuse, who are marginalized. What's the definition of marginalized? They're literally pushed to the edges, right, out of the field of consciousness. So on both the environmental and the social, we have to somehow recalibrate our cognition to move these things back into the centerpiece. And I know this is abstract, but so rather, it's very non-technical. I'm just speaking to you not as students of CS or as people interested in social impact, but rather just as humans. So what else is going on the Earth? So we're doing this, we're doing this back and forth. And and that's creating this level of change that the philosopher Timothy Morton calls hyper-objects. These are systems that are changing, that are bigger than us, way bigger than us. They're bigger than a human lifetime. They're bigger than individual agency. They require lots of collective action, and they're moving at speeds, frequencies, and locations that are outside of our cognition. So, for instance, we use about 1/3 of the world's landmass to feed ourselves today. And as we cultivate, and like if you just look here, that's what we're doing. We're cutting down all the forest. In this case, we might be planting it with food crops for us or for livestock. And as we do, we actually squeeze the habitats for wildlife, and we increase the interactions between wildlife and livestock and human beings, which is a major vector for new zoonotic illnesses. Now, I don't know where COVID came from, but I can tell you that SARS and MERS and things came before come from the interactions between those systems. So as we put pressure on those systems, we think about these as public health challenges, and then we socialize them as social problems, right? But the reality is that foundationally, they're ecological problems. They're actually in the relationship between how we are using the Earth. And it gets worse from here. So if any of you, I'm just going to say it right off the bat, the next 6 slides are kind of depressing, okay? Because at the same time, we're causing a major extinction on the Earth. We are likely in the 6th extinction, the 6th time in the history of life on Earth when biodiversity has collapsed. The last time was 60 million years ago when a giant meteor hit the Yucatan. If we were doing the kindergarten school play of the dinosaur and the meteorite, we would be cast as the meteor. Okay? We're causing this. We like to say things. We have things in vernacular English. There's always another fish in the sea. Well, in some cases, there may not be more fish in the sea. In some parts of Asia Pacific, for instance, we're just wiping out all the fish in the ocean on a material basis, right? And that's all before we get to climate change and what we're doing to this kangaroo, right? We're burning the planet alive at this moment. Our friends at the Intergovernmental Panel on Climate Change have told us that we have, at this point, we are living through the most important decade in history in terms of the climate, in all of human history. Because the decisions we make in this very narrow window will either lock in or avoid the worst effects of climate change. In fact, they gave us 5 fundamental scientifically driven scenarios for life to the end of the century. And in 4 of them, big chunks of the planet become uninhabitable for your kids and grandkids. The ones you have not had yet, most of you, but certainly mine, right? There's only one path that actually gets us to a more equitable, just, and stabilized future for all living things and all of the different parts of the communities human communities that we exist among in between. And that requires us to act literally this minute. Like, we have to start right now. This is the most important day in the most important year for climate action, because tomorrow we have less agency than we have today. And every day thereafter, it diminishes a little bit as we lock things in. And that's just one of 9 major systems on Earth that actually make it possible for life to flourish. This is work done by the Stockholm Resilience Institute and now done at Potsdam Institute for Climate. There are 9 foundational systems that make it possible for life to flourish on the Earth. 4 of them have been pushed past the planet's natural regenerative capacity. So we're literally snipping the threads in the common bonds that make it possible for us to live on the Earth right now. And that is all before we add another billion people to the planet in this decade. It took us hundreds of thousands of years to get to the first billion modern humans. We're going to add the last billion modern humans in 10 years. So we've got to do all of this in a time of spikes where the world is going vertical, right? The number of people on the planet, the amount of carbon in the atmosphere, the number of McDonald's restaurants, you pick a metric, they're all going like this because they're all derivative of us. So here's the interesting moment that we're in. If I stopped my talk now, we would all be forgiven for being really bummed out for the rest of the day. It's like, I can give you a film strip of doom, okay? But while we're living in the early days of the 6th extinction, it's also the case that we're living through the 2nd Renaissance. We're living through this explosion of human capacity, human capability, human infrastructure, and now especially because of some of the work that's beginning to happen where we're really beginning to catch a wave coming out of I think it's probably not quite an AI summer, but it's maybe an AI spring, right? So we're in a place where we've got extraordinarily powerful tools and extraordinarily big problems that are literally bigger than our cognition. Like the stuff that I showed you at the very beginning, the flickering images, they're bigger than our ability to see and think of. If I tried to tell you that we have large language models that are trained on 50 billion data points. You can't imagine 50 billion data points. You can't imagine a million species at risk. You can't imagine a billion people in a decade. Those problems are like the set size is too large for our cognition. But what we know is that if we have these really powerful tools on one end and we have these really powerful problems on another, we have a moral, not just a commercial obligation to align those two things, right? And that's really why we as an organization exist. And let me tell you how that works, okay? So I'm going to show you a lot of stuff about space and satellites and AI and how they converge to help us address those challenges that I just showed you, right? To get some traction on these problems. And a good example of this is what you can do when you begin to look down. We're going to pick one problem, which is agriculture. And the reason I wanted to show this is because right at the beginning, remember I showed you we're using 1/3 of the land's surface to feed ourselves, and we have 1 billion new people showing up at humanity's restaurant in this decade, right? And that's going to put enormous pressure on the forest. The field-to-forest boundary becomes contested, and it's important for climate, it's important for indigenous peoples, and it's important for wildlife, all of those things, all parts of the web of life. So let's take a typical farmer, say in Iowa, right? If you're growing corn in Iowa, you're sort of running an IT shop that happens to grow things. And those farmers pull in all kinds of information. And what we can do with satellites is we can actually look and tell them precisely when to plant, and precisely how much water to apply, and precisely how much fertilizer to use or not to use, to maintain or increase their yields, right? And that's important because every liter of nitrogen-based fertilizer has to be made with heavy industry, with enormous carbon emissions. It has to be transported to the field, has to be poured on the crops, runs off the crops into the Mississippi River, comes down the Mississippi River, and all of the loaded nitrogen water in the Gulf of the Mississippi creates a dead zone the size of New Jersey where no living thing can exist, right? So if you can use information intensivity, if we can use the power to extract and apply signals intelligence to use one less liter of nitrogen fertilizer, that's one less liter that needs to go through that whole cycle, right? So what we do is we use information intensivity to decrease ecological intensivity. That's the basic mechanism. And if there's one supercharged application of AI to planetary problems, it's this one, right? If we can get really good at all of the creating a signal in the midst of uncertainty and complexity and other, that's some of the research that's actually happening in this very place. I have applied problems for those techniques today, right, that look like this. And the result is we get more people fed on the same or less land, and we begin to create opportunities for the planet to recover, and we get through this chaotic system of transition. So I was asked to say a few words about Planet. This is not an advertisement for Planet. I'm going to show you stuff, but I just want you to get a sense for what we do, because we're at the edge of this. And we work with alums of this very institution on a lot of stuff. I will just tell you, up at Microsoft, you'll hear a couple of examples of that in this talk. So I just want to say a couple things about our organization. So we are what's called a public benefit corporation. It's a specialized institutional structure that requires us to produce more value for shareholders than mere return, for more return for stakeholders than return for shareholders. It actually requires us to define and document a public benefit purpose, and then to report on our progress in fulfilling that purpose, which is a non-commercial purpose. So what it allows us to do is sort of hybridize between a nonprofit and a for-profit kind of enterprise. And it allows us to make decisions, among many other things, to do things that are not in our shareholders' immediate return sometimes, but are in the long-term value of our stakeholders. And we define those stakeholders to include life on Earth. So we're an organization named Planet, and we are also for the planet. We are here to build a system that allows us to build those kinds of feedback loops. How many people here are aerospace engineers? Half one. Kind of did this, okay? Yeah? You're almost there. Okay. So we have almost one in the room. Okay, so for those of you who are not aerospace engineers and not very familiar with satellites, so this is going to start with satellites, it's going to end with AI, but we're going to go on that trajectory, okay? So I want to just show you what a typical Earth observation satellite looks like. It's about the size of a small school bus. It's covered in gold reflective thermal coverings, and you can literally see people crawling on them. So the issue with these instruments is that they cost hundreds of millions to billions of dollars to design and build. They take decades of planning. And sometimes they blow up on the launch pad. So they're very conservatively built. They're designed to last a very long time because they're kind of like mainframe computers in space. They're like rugged and robust and designed to operate for long periods of time. And I will say they are exquisite instruments. If you could spend $1 billion building a satellite that took pictures of the Earth, this would be an amazing example of what you could build, right? It's like the Hubble or the James Webb telescopes, like these are like huge achievements. But if you are a young aerospace engineer, the challenge is that, these don't come along all that often. And so if you're going to build one of these, you might get to work on 2 in your whole career. So these are a group of young engineers, like young engineering students and early career professionals, and they said, we want to do something differently. So they went down to Best Buy. Do you all know what Best Buy is? You've heard of Best Buy? Yeah, I thought so. Okay, and they bought a stack of these things, and they took them back to the lab. They took the guts out of the phone. They built a tiny little satellite you can fit in the palm of your hand, and they secretly gave it to one of the astronauts who's headed to the International Space Station and asked her to throw it out the airlock when she got there to see how your phone would do in space. And they got caught a few weeks beforehand and all nearly fired. And then the higher-ups very wisely said, we will allow you to continue this. So they took that little instrument out of the vest pocket of the spacesuit of the astronaut and said, when you get there, okay, let's put it into space. And it turns out your phone does great in space. If it's shielded correctly, it has a camera, a computer, a GPS, a radio. It has all the things that these giant instruments have in a tiny little package because we spent trillions of dollars here on Earth to make these things very small and energy efficient, things like that. And that led to a revolution in the design of satellites that look like this. This is about the size of a loaf of bread. So instead of a school bus, when you make things small, you can make them cheap. You can make them, you can make many of them instead of making just one. And you can do things that you couldn't do before. So one of the things is you might have only 1 or 2 of those big instruments, right? And those big instruments don't get to see everywhere every day. So what these satellites do is something very different. So I want you to imagine you're the sun, here's the Earth, just kindergarten refresher, it's spinning around on a daily basis. It goes around the sun, on an annual basis on a slight tilt. And what these satellites do is they spin from pole to pole. And as the Earth turns perpendicularly underneath them, they act as a line scanner for the planet. So we see every place on Earth. And are there any astronauts in the room? I'm just curious. Okay, there are no astronauts. Every place you've ever been, for roughly the last 2,000 days, we've been taking a picture at lunchtime from directly overhead. Today, the building we're in, and every other place you've been at roughly lunchtime today. It was not cloudy today, so we were talking about this over lunch like it had just happened, right? So satellites that look at the Earth are differentiated in 3 core dimensions. Their spatial resolution, how zoomed in do they get? Their temporal resolution, how often do they come back to see the same place? And their spectral resolution, how much light do they see beyond what the human eye can see? We have 2 systems today, one that images the whole Earth every day at like 3 meters per pixel. So it's, like this whole room would be like 25 pixels, and not a very high resolution picture, but enough to see what it was. But really, really high temporal resolution, very high, like a time series of information of change. And then we have other instruments that zoom in to about 50 to 30 centimeters that can take a picture of like roughly you sitting in your chair. Again, we can't tell who you are. We're not interested in spying on you, but we're really interested in understanding what's happening. We use these 2 things together. In fact, we use AI to detect anomalies at the 3-meter data and then zoom in and task the higher resolution ones to take pictures of stuff that's of interest. And what we're doing is we're taking all that data and we're extracting all this information about where all the carbon and the water and the biomass and the human footprint and all of these activities are. And let me just give you a simple example of this. This is one of those a mosaic of satellite imagery taken over a few days to strip out all the clouds. And then we use supervised machine learning techniques to extract all the buildings in blue and all the roads in red of our little corner of San Francisco, where offices are actually down in the lower right corner of this screen. But because we're able to do that on this analytical layer, we can do it not just for our corner of San Francisco, but we can do it for every road and every building on Earth that day, or every few days. Now, think about what that means for detecting change. Right? Let me give you an example. Just a few days ago, there was a massive earthquake in Turkey. These are 2 of the actual satellite images looking down just before and just after the quake, the day before and the day after. And it turns out having the information the day before is just as important for baselining where the system was, so you can understand what's changed. And then running those very same kinds of machine learning techniques over the imagery, we can identify every single building that fell down. This is way more powerful than being able to do it with drones. Like all these other things you have to do on the ground, this passively can just occur. And what that allows is a feedback loop to send the scarce resource, and that's the humanitarian aid worker and the disaster response agency, to the right place at the right time, right? Because you only have so many of them in the immediate aftermath. And you can think about what it means for reconstruction and a million other things like that. Here's another example of this and what it means for social protection. So we have communities of people who are farmers all over the world who are smallholder farmers. And those smallholder farmers are often exquisitely vulnerable to climate risk. Or pastoralists who are moving their herds, also extremely vulnerable to climate-exacerbated shocks and disruptions. And those shocks and disruptions show up as things like drought, or they show up as flooding. And so what one of the tools that we have is a tool that allows us to detect those kinds of events, flooding events and changes in soil moisture. And for this particular group of people, working with an insurance organization, they've provided low-cost insurance to those pastoralists in case their livestock their herds are affected by flood. So they're very, very affected. They're very at risk, right? But the challenge is they're very, very hard to reach because they don't have fixed addresses. They're moving around all the time through the landscape. So how do you reach them? Well, now all these pastoralists have mobile phones. So what happens is we can detect where they are and we can detect where the flooding is, and we create an index, what's called an index insurance product. And when the index is crossed, there are automatic payouts made to their mobile accounts to compensate them for their loss. And that's how you keep, because the thing about an age of volatility and disruption is that volatility does one of its signature effects is it erases progress. It pushes people backwards. Right? So the question is, how do you build mechanisms that allow people to compensate for those kinds of deleterious effects in a system and to maintain something closer to a dynamic disequilibrium around a more fixed point rather than having these shocks come after? Here's another example. This is we do a huge amount of work with a team that's based at the University of Maryland called NASA Harvest. And we worked with them in the context of Ukraine during the course of the conflict to map every single field in the entire country in real time and measure its agricultural productivity. Now, I'll tell you why that's important. We were just talking about the Turkey quake a minute ago. So the World Food Program, the UN's agency that delivers food aid, one of the principal ones, gets 40% of the food that they deliver from Ukraine. So when the conflict in Ukraine happens, it causes a delayed reaction of food scarcity all over the world, but in places that are very hard to predict. So you really want to understand how to blunt the edges of that disruption. And so what we did with them was this massive project that provided real-time agricultural policy-grade indicators about what was happening, both to the government, to all the food entities around the world, so that people could effectively plan for an anticipated shock. This shock not caused by climate, but caused by conflict. In fact, you can actually see here, this is all derivatives of the satellite imagery. Literally every one of those dots that's blinking is harvesting activity or not harvesting activity that's happening in every one of those fields. So this is, one of the kind of meta themes that you'll hear me talk about before we get into the AI side of this is that we need feedback loops, that when you're in a period of volatility, and for the rest of our lives we're going to be in a period of volatility, you need feedback loops that move as fast as the forces of change that are happening on a system. So I was sharing this with some of the grad students. When you're building a satellite, you actually have to measure the forces working on the satellite as fast as those forces are working on the satellite. Because otherwise, if you're just measuring its position every 5 minutes, it could tumble out of orbit before you are able, you get into an uncontrollable spin, right? Does that make sense? So you have to measure it all the time, continuously, faster than it can move. Well, we live on a satellite. It just happens to be one that's going around the sun and have 8 billion friends and relations as fellow astronauts. And those instruments, we need instruments that allow us to measure change on the planet so that, among other things, we can take the people who are most exposed to those disruptions and help mitigate the effects of them. And so, for instance, this kind of information is being used today to feed Ukrainians as well as the world. Other work that's going on in Ukraine is being used to assess damage to every building, just like we're doing in the Turkey example, to ensure that people can safely be repatriated back to Ukraine. All of those things are about dealing with these disruptions and creating greater resilience. And then you have my single favorite example in the whole talk I'm going to give you today. That's over there on the left. This is Cheyenne Christensen. He's an organic dairy farmer from rural Wisconsin, and my family and I live in Minnesota. And Cheyenne is an organic dairy farmer. They're trying to he and I don't know if you've ever heard of Organic Valley. Do you ever heard of it? Some of you nod your heads, right? Organic Valley is a huge cooperative of family farms that are trying to reintroduce these deeply organic and sustainable practices to rebuild the land and the soil content, right? Which is to practice a forms of agriculture, very ancient forms of agriculture. And it just so happens that Cheyenne makes the milk, his cows, sorry, the middle image there, that's not Cheyenne making the milk, that's the cow making the milk, makes the milk that I actually drink every morning with my kids as we're getting ready for school. Like, this is the cow, or one of them, that produces the milk, that goes in the bottle, that comes to the store. That's my actual store. That's the other end of the supply chain, of the milk supply chain. It literally goes into neighboring Wisconsin, then it comes to my town, and I buy it at that shop, and it comes from his farm. And one of the ways in which the practices they're trying to reestablish are organic farming practices, really simple farming practices, where they rotate, as the grass is growing in the field, in the pasture, they rotate the cows around the fields. And the precise ordering where they move the cows around is determined by this thing that he's holding in his hand, which is a kind of heat map of the growth of his pastures as measured from space. So the supply chain for my milk goes from that cow to space, or I should say, it goes from space to the cow, to the farmer, to the cow, to the milk, to the store, to me, right? Which is kind of amazing, I just think. And in this way, we're actually able to help reintroduce these very old but deeply sustainable practices. And interestingly, about a third of the farmers that we serve with this capability are Amish. And so we have to physically mail them the satellite imagery. They can use it, but they can't receive it digitally. So we send it to them indirectly. Okay, so now let me get back to stuff that looks at the health of this world. So I want to show you a picture. This is a solution to the problem I was showing you of the perceptual problem. So this is a picture of deforestation deep in the Amazon. It's a few weeks of deforestation sped up in one place. I wanted to show you the raw imagery. This is like just a film strip of what comes out of the instruments. You can see there's clouds sometimes and strip things and stuff like that. But what you can see very clearly is this is illegal deforestation. This is what it looks like when you take something that's slow and big and abstract and far away and you move it into the perceptual frequency of human cognition. You go, oh, well, that's terrible, right? We need to do something about that because transparency is the beginning of accountability. So being able to see things is the very first step in taking responsibility for changing them. Now, like you, the first time I was shown this, I paid attention to what's on the right-hand side of the screen, which you might not have seen in the same way that we don't see the other forms of changes. What happens right after that deforestation occurs? On the left-hand side of the screen, you'll see these little spider webs come out. Those little spider webs are the illegal roads that go in before the next round of deforestation begins. They're what you do is you build an illegal road with your tractors into the forest so that you have the equipment in there to take the timber out and to engage, in this case, in deforestation where it is absolutely prohibited. And we can train computer vision, supervised machine learning techniques to find these roads, which is exactly what we do for environmental police, who have now deployed 3,300 agents being fed by that algorithm in real time. So the satellites are looking at the Amazon. They're identifying where the illegal roads are. The algorithm is extracting the road pattern and then feeding the prioritization stack for raids, where they literally parachute in and they blow up the trucks, and then they arrest the people and they confiscate all of their stuff. They've confiscated nearly $2 billion by using AI to drive behavior on the ground in the support of and preservation of the forests. So that's what we're talking about. We're talking about taking the invisible, making it visible, taking the visible and making it actionable. And as we go from the invisible to the visible, that's the data side. As we go from visible to accessible and actionable, that's the AI side. So that's the algorithmic applications that we're beginning to see. And I could give you bajillions of others, but I want to give you one other one on forests because it's also not all a film strip of doom. We also have to be good at identifying, and you, as some of you as social scientists and computer science know, we need to identify what works, and we need evidence of what works. And here's a really good example of what works that you can really only see from this perspective. You can see all that deforestation. It's literally like it's like an invading virus, right? It's like some kind of necrotic infection or something on the landscape, and then it stops. And the place it stops is an indigenous reserve, because the people that live there, there's an institution called IPBES. It's the Global Institute that measures biodiversity and nature, and everywhere on the planet, biodiversity is being lost. Everywhere. The only place where there's a brief glimmer of hope is where indigenous peoples have stewardship over the land. And you can literally see evidence of it here, right? It's what happens when you give people equity in the system. This is a demonstration of equity. It's a demonstration of parity of rights and what happens, what it means not just for them, but for the places that they steward. So we have a huge program, I won't say more about it, where we take all of the data. This is actually, I will say this. We take all the data that we collect about all the forests between 30 degrees north and south. That's the tropical belt of the Earth. And we make all of it available as a public good to all of the governments that are contained therein and the UN and countless NGOs, so that there's one standard for understanding deforestation on the Earth across the tropical belt. So that's what you can do when you're a public benefit corporation. You can balance the ways in which you produce revenue and the ways in which you create public good. And we're doing all kinds of other things besides extracting information, not just about where the trees are, but how much carbon is in the landscape. This is, again, extremely sophisticated machine learning and AI techniques that combine. So this is what we do here. Here's a picture of some forest. And there's satellite imagery, and there's another form of remote sensing called airborne LiDAR. LiDAR is the instrument on a self-driving car that spins around. Sometimes you see these little things spinning at the top. What it's doing is it's creating a point cloud, a volumetric point cloud around the car that tells you where it is in space. And what this does is combine strips of LiDAR with large areas, extrapolates where we have satellite imagery and LiDAR to places where we only have satellite imagery, and it allows us to build a volumetric structure of the forest by pointing that instrument at the ground and then extrapolating. And what you get is a map, first of what the three-dimensional structure of the forest is, and then you get a map of where all the carbon is. And the reason that map of carbon is so important is because if we're going to keep carbon in the ground, it's one of the ways we're going to solve the problem of climate change. We have to preserve the carbon where it is. And this is a central strategy for independently monitoring and verifying where all those environmental activities are. And then once you have that model of the forest canopy, then you can do things like this, where you can run very large-scale wildfire simulations under a variety of scenarios. This is 200 million wildfire simulations run over this particular strip of forests in California. This is the highest resolution map of wildfire risk that exists for any place on the Earth. This place right here, this image I'm showing you, is part of a larger map of the entire state of California. We produced that down to a few meters. And the reason that's important is because it allows us to mitigate wildfire risk. It allows us to target where we're going to do interventions, like we're going to do controlled burns, we're going to reduce fuel loads. All of those activities come when you're able to see what you're looking at. And we've done this in all kinds of areas, like monitoring all the world's coral reefs would be a good example. And this is one of my other favorite examples, driven by AI. This is a coalition of actors that we work with very closely called Climate Trace. And what they're doing is they're monitoring coal-fired power plants, among other things. They're building a completely independent measurement system for the climate. And it's all powered by satellite imagery. So here's an example. They look at a coal-fired power plant. Governments don't report what coal-fired power plants emit into the atmosphere. So when you're trying to negotiate a solution to climate change at one of the big climate summits that the UN holds, people don't have good information about them. So in this case, that's partly because the plants turn on and off, and as they turn on and off, their emissions are very variable. So what they built was a system that allows them to identify coal-fired power plants, monitor when they're turned on and off in the satellite imagery, and feed those into a machine learning model that estimates their emissions. And if you can do it for one, you can do it for all. So they've actually now done this for all the world's coal-fired power plants. So we now have an independent, non-governmental source of truth for how emissions are unfolding. And actually what you see here, this is one of these instruments it's one of these coal-fired power plants in India. This is the emissions profile over the last year from this plant. So you can imagine, again, all of the sort of the central theme of all of this is you can't optimize what you don't measure, right? And so, and this has been a problem all throughout. And I'll just come I have a couple more examples, and then I'm going to stop. And hopefully, this is a small enough group we could have a real chat. But coming this year are actually breakthrough new technologies that are going to directly measure emissions from the atmosphere, instead of trying to infer them. This is an instrument that we're just launching now called Tanager, which directly measures methane emissions in the atmosphere and directly measures particulate emissions in the atmosphere. And it sees in more than 400 bands of light. And when you combine the optical imagery with satellite, this methane emissions are molecule for molecule much worse than carbon emissions. They're not as big a contributor as carbon, but they're hugely important. So shutting down excessive methane emissions is really important, but methane is invisible, odorless. It's hard to know where it's occurring. Well, we can make the invisible visible, then we can literally attach it to a particular place and say we know exactly which facility it's coming from. We know, given the wind speed and the direction, precisely the point at which it's being emitted. So this is an effort between a group of climate philanthropists, Planet, NASA's Jet Propulsion Laboratory, and the state of California. So why is the state of California involved? Because if we can make detecting methane emissions dirt cheap, they can make ignoring them incredibly expensive, right? And so you can build incentives, architectures, and policies. And again, this is all the same thing over and over and over again. In fact, that very same instrument, I'll tell you, can be used for just the other really big use cases in biodiversity assessment. When you point a hyperspectral instrument down and you look at a patch of trees or plants that might look green, they all look green to you and I, but they fluoresce in all these different bandwidths of light completely differently. You can tell that this is one subspecies and this is another subspecies. So here, just for example, is a portion of Peru, and it all looks green when you look at Google Earth, but when you light it up with these instruments, you suddenly see all the texture of biodiversity. And again, you can't protect biodiversity if you can't measure biodiversity. And those are all of the things. So what we're moving now is from a place where we're building the ability to detect, classify, assess, and then distribute, and then plug into the kind of policy architectures like I showed you, those insurance programs or social protection schemes. Caleb Robinson, who's a graduate of this place? He was a visiting PhD student. Now up at Microsoft, his team and we work together very closely. This is one example where we're using computer vision techniques and supervised machine learning to identify every single renewable energy resource on the planet on a timeline, going backwards to 2018 and forwards to 2030, so we can track our progress in the positive direction. So this is actually the satellite imagery zooming in on the same part of India. We find all of these little blue dots are the windmills, and all of the orange elements are the renewable energy resources. And because we know when they happened, we can tell you how much energy they're producing because we know which version of the solar and wind technologies they're implementing based on when they were built. So there's this sort of like, I think the thing that's really interesting to me is that for those of you who are working on core AI technologies here, there is going to be an extraordinary abundance of data and the ability to build tools that guide policy or that sometimes create automated policies that I think are just as powerful. And all of that, everything I've been talking to you about is all about the classification side of AI. It's all about, we have large unstructured data sets. They look like the planet, right? We have them in high enough resolution to actually run real classification schemes now for everything. And at the same time is the other side of the story. And again, this is like from an industry perspective, which is what's happening on the generative side. And it's actually not so much the generative side. We don't want to generate fake imagery. What we want to do is be able to ask transformational questions of that imagery using semantic search. So instead of, because this is a central problem, that whenever you invent a new technology, and you, like I literally yesterday was at the World Bank in Washington, D.C., and the central question everyone has is what's called the capacity question. The institutions that we want to empower don't have PhD computer scientists in them, so how are they going to be able to use this technology, right? And if they can't use it, they will be disenfranchised from it, and the inequality will grow between them and the entities that can. You know, if you have two groups in a society, the already powerful and usually the much larger group of people who are already marginalized, and you release very powerful technologies even for free, what you typically do is you super empower the already super empowered, and you marginally improve the position of the rest, and the net inequality grows between them. But what's really interesting about that question is this. Nobody asked that question about Google, because Google did a couple things. They indexed the internet, which is equivalent to what we're talking about here. We're indexing the planet. And then they put it behind the world's easiest and simplest and kind of dumbest user interface you could possibly imagine, the search bar, so you could literally just go like this until you got the answer that you wanted. So no one asks the capacity. Like, no one says, okay, Google could have stopped at the index of the Earth and then said, now every NGO and nonprofit that's working in social policy or the delivery of services just has to hire a library scientist, and they're going to get all this value, right? And we wouldn't have Google as we understand it today. But what I'm here to tell you is that the things we're seeing on the, you know, you can use all the different large language models or kind of deep learning, or especially just sort of semantic, like deeply contextual search. When wedded to this, we're about to see a sea change, because people will be asking questions of the planet and getting answers maybe without ever seeing the stuff that's underneath, right? Without ever seeing the data sets and the fancy pixels that I showed you, right? It will just become as natural to know something about the Earth as it is to know something about something that's in a, you know, in a Nature paper. You know what I mean? It's as accessible to everybody. So that's really exciting. And for those of you who are near leaving, that is the moment when we go from small, technical, interesting, powerful for the few to potentially transformational for the many. And you're like right on the cusp of that. You know what I mean? Like you're like new players entering the field, some of you who might graduate out of this and go into industry, but even if you aren't, like, no matter what you do, you stay in academia, you don't stay in academia, this is going to happen. And it's going to happen like in the foreseeable next, I don't know, 36 months, right? Or 48 months, like next 3 or 4 years. This is going to become a real practical exercise for all kinds of things, and we're going to be able to build really different ways of enabling kind of stewardship of the planet. I think this is, yeah, okay. There's a slide that's missing in here, but I just wanted to say one of the things that makes me very excited is the natural opportunities to to diversify our politics around these technologies. We must always preserve and protect privacy, for instance. But what's really interesting to me is that in a lot of the places where we work and see the greatest effects of the distribution of these tools, it's with people who are not included on the map, who want the right to be included, not the right to be excluded. Because their starting place is either less visibility and less social agency. So I think there's an extraordinary opportunity to begin to think about the spatial dimensions of inequality and to think about through the mechanisms of these machines, how do we do that? But I wanted to leave you I think there's sort of two really big ideas here. So the first one is the ability to actually fundamentally, structurally change these systems in their root, rather than just at their edges of their worst deleterious effects. So for example, if you take capitalism itself, capitalism has produced unrivaled wealth for some people on Earth. But in its foundations, it's always been sort of incomplete because, among other things, it's treated certain things as externalities. That's the actual term. They're just not included. So like the value of the water, the river, the streams, the fish, the other living organisms are just inconsequential, right? We've always treated nature as if it were self-replenishing, hyper-abundant, and free. So if you bespoil this river, you just go to the next river. And then when you bespoil that river, you go to the next river. And that might have been true in the earliest days of capitalism, when we lived in what was effectively a much larger planet than the one we live on now, but it's not true now. And so that what you end up with is this weird thing where, the company Amazon is measured billions of times a day to a fraction of a penny. But the actual Amazon for which it's named has no actual economic value whatsoever until the trees are cut down and cleared to do the things I was showing you before. But these tools are a central mechanism for creating internalities, and not just at the environmental level, but at the social level. They are ways of enabling those things that have been excluded, marginalized, and devalued to be understood as part of a more comprehensive whole. And I think that is the moral aspiration that is at the center of this technical exercise, no matter what side of it you sit on. Whether you're a technical person and you're building core machine learning, research and development, or whether you're thinking about applications for social change. Ultimately, what we're talking about here is seeing the whole. Ecologists, who I work a lot with, have this question that they sometimes ask: why do humans and birds and bees and fish and other animals, why do we flock together? Why do we swarm? Like, have you ever been scuba? I don't know if you've ever seen the nature documentary. You see these like big, slow-moving like minnows, giant schools of fish. Like, it makes absolutely no sense. If you're a big fish, you're like, there's lunch all collected in one place. Why on earth would we do that? Well, part of the reason we do that is, all of us, birds, bees, fish, and humans, is because every single perspective, every single organism connected in a superorganism sees a slightly different perspective. And if you can signal within the group quickly enough, you can essentially see in a panopticon and reduce the risk of predation, which is why the big fish comes along and all the little fish dart out of the way simultaneously, right? Because having lots of eyes on the process and lots of eyes on the problem is a way of creating collective safety. And it's a central opportunity that exists with these tools that you are building, right, to create debiased models that overcome the limits of perception, is also the limits of our ecological and our social perception of what counts and who matters. And distributing them to everybody is the mechanism by which we create more collective safety in a world in which we are foundationally, if not always, aware of just how interconnected we actually are. And that is the end of my talk. Thanks very much for that. And I'm happy to take questions about anything, including what I had for lunch today. I don't know how much time we have left, but I thought I would just do relatively short. Yeah.
Yeah, I mean, we are at the end of if anybody has questions, please. Yeah, and you
Well, the rate limiting factor, well, let me start with this. Any material statement that you can make about artificial intelligence, and I'm talking about from an informed perspective, across both the classification, like this is wildly large-scale data sets and remote sensing and real-time information plugged into incredibly sophisticated algorithms, both on the classification and kind of generative side of things, right? And that story is going to be, no institution will be untouched. In the same way that no institution was untouched by the rise of mass communication, right? The way we do things, but it's going to change. And so I'll come to specific applications in a minute. But let me just say to you that the challenge with these extraordinary superpowers that we're talking about is that almost any statement you make about them is true. So they will be used to tell the truth in unprecedented ways, and they will be used to lie in unprecedented ways. They will be used as a tool of peace. They will be used as a tool of war. They will be used to include, and they will be used to exclude, right? So because human nature doesn't change, what we're doing is we're moving by several standard deviations the technological capability of both our better angels and our worst demons. So that is a hard, the thing that is important is how do you then make sure that you're building intentional institutions so that, this is going to really date me, but a long time ago there was a folk singer named Ani DeFranco. Does anybody here know who Ani DeFranco is? Yeah, she's a great line in one of her songs, "Every tool is a weapon if you hold it right." And it's very aptly applied to these tools. So I am incredibly excited about, this is why we have intentionally sort of hedged in the direction of values-based applications. It's why we are careful to audit and run incredibly sophisticated ethical review processes on applications to ensure that we will not be able to stop its weaponization completely because we can't stop human nature completely, and people are clever. But we can ensure that if we're very intentional about it, that we hope that the positive applications will outweigh the bad ones. So what are the ones that I think are really exciting right now? I'm going to tell you a kind of a sorry answer, because the most exciting and most important things that are going to happen, and they're literally happening at this moment, are really boring. They're the opposite of the charismatic problem. So a good example of this would be population. We don't know where everybody on Earth is. We know roughly how many people are where, but there are, we have a big partnership with an entity called the Institute for Health Metrics and Evaluation, which is a big Gates-funded center at the University of Washington, and they're population health experts. And we just had a meeting with them and the World Health Organization. COVID is worst among the last 10%. It's the last 10% of COVID is the hardest part of COVID. But a big part of why it's hard is because we don't know where the people are who have it. We don't see them, and they're spatially arranged, right? So if you take a place like, I was going to show this graphic, actually, is the thing I didn't show. But I have a friend who's an economist at Stanford, and he did this. I'll show the graphic in a minute, but it's a picture of Africa, and it shows the rate at which we've done household survey and demographic assessment of these countries. And there are big holes in the map where the answer is never. These countries have done no census, no regular households. You can't run an economy. You can't lift people out of poverty if you don't know where they are, and you don't even know if they are, and kind of like all that kind of stuff. And what's particularly interesting is that these are some of the places that are growing fastest in the world. They're growing like 15% a year, every year. So if the last picture you had of them is 10 years old, the situation is radically different, even if the last picture was 3 years old. So one of the very first things we're doing in population health is just finding all of the population, right? it turns out to be exquisitely relevant to a whole bunch of problems. And I could go on with problems like that, but the idea is like the foundational building blocks of the higher order systems and those kind of real-time feedback loops start with basic primitives, really understanding kind of those basic mechanics and inventorying the world. So I think that's a particularly exciting one. If I had to, and I guess the only thing I think I'd say is that I think the most exciting thing that's about to happen is the hookup of the, well, let me back up. We built Planet specifically with the idea that we were building a kind of moral mirror that we're holding up to humanity to allow ourselves to see ourselves in context, to see the consequences of our actions. The ability to hook that up to the most easy-to-use interface means that people will ask questions that I can't answer or couldn't conceive of, and that's really incredibly exciting. Oh.
Technical question.
Well, I have a very non-technical answer.
Well, the two non-technical questions. So the first one is to understand sort of your funding model. How do you exist? Who supports you? And second is an understanding of kind of your org chart, like what percentage of you are machine learning people versus et cetera.
Can you hold the mic a little closer?
Kind of how does your organization get divided up in terms of skills?
I heard the first question was about funding, and the second question...
So what percentage of you are computer scientists?
Oh, yeah. Great question. Okay, so I can give you all that stuff. That's easy. So first of all, we're weird because we're funded by the creme de la creme of Silicon Valley venture capital and multilateral institutions like the World Bank, and a bunch of triple bottom line philanthropic and social impact investors who were all instrumental in helping us craft this organizational structure that is somewhat unconventional. We're one of a handful of publicly traded, we're now on we went public a year ago, public benefit corporations. So the idea is to try to, I think it's also worth noting, like think of all the tech giants in the world today. I don't have to mention them, and I'd rather not. But think about those big organizations, right? We let them become big organizations in very significant part because we exempted them from certain forms of responsibility. And then they became so big that then they were like, wait a second, there's only so much of this we can do now that we're big. I mean, it's really hard now that we've got billions of people to serve, to filter out all the stuff that's terrible. And now we're fighting about who's responsible for what when somebody posts something online in one of those big platforms, just as an example. Okay, what we're trying to do is grow, and we set this expectation at the beginning where the mission of the organization and the funding and the technology would all be intertwined and inseparable. And becoming a public benefit corporation was a way of making it hard to undo those things so that we couldn't be bought out by a bunch of anonymous tan pants wearing certain kind of guys of a certain age that nobody wants to hang out with. Okay, so there's that. And then I think the second question is like kind of our organizational structure. So if you look at what we do, we design and build and manufacture satellites, and we operate them, and we run we have 50 ground control stations all over the world, the domes that are looking, and there are amazing stories I could tell you about all the crazy ways in which we've repurposed old Cold War assets to like use them for humanitarian purposes, and I could do all kinds of stuff. And then we are collecting all that data, and then we're building software platforms, and we're hosting it in the cloud, and we have all this data pipeline and processing information, and then jobs to do, and then we're running analytics, and we're extracting that information, and then we're partnering with organizations that are on the front lines, and there are thousands of them that we work with, to do all kinds of stuff. And if I had to say, like, the purely technical side of I'm core computer science engineering, AI, platform, software development is probably half the organization. And we're talking about, about 1,000 people, right? Then you've got 300, 400 people that are selling that stuff and marketing that stuff and making sure it's a going concern. And then the third thing, when you get to the group of people that actually catalyze these kinds of outcomes, it's actually quite small. But partly we can be that way because we have a very, very powerful thing that can only be actualized in collaborative structures. Like, notice, I didn't stand up here and say, planet is saving the forests. It's not us, right? What we have to do, and this is a mistake that technology organizations make a lot, actually. We're happy to be anonymous because what we're measuring is not our fame. We're measuring how are we doing against these problems. So as a consequence of that, we want to take the institutions that have the mandate, the position, the closeness to the community of need, which we don't have, right? And we want to super empower them. And that means working in coalitions with funders and donors and scientists and technical people and governments and indigenous peoples and their representatives and local communities of all different stripes and being equals at the same table, right? And so I'll just say, like, these tools have very powerful, I showed that indigenous example, right? And it's worth noting that we have this very powerful tool precisely it's not a silver bullet, it's part of a set of things that matter, but they come about at a time when they're really needed. But they also come about after, like, in the context of those indigenous conversations, 500 years of colonialism and of people showing up from the North and West saying, hey, I've got a solution for you. I want you to buy this, buy my tech, my book, my religion, my governance system, my whatever. And there's all kinds of trust issues there. And if we want to be effective and fast, we have to work with the fabric. Like the rate limiting factor for these solutions, and you know this if you work on the social side of the social problems that CAIS thinks about, is trust. It's whether or not you have a credible message and a credible messenger and you are in coalition and relation. So we work a lot on that. That's actually, the interesting thing is that it's a lot of people who know about the problem spaces, but we're mostly building coalitions of the willing and then trying to figure out how to technologically enable them. None of the things I showed you live at Planet, for instance. They all live out in the world. They belong to the institutions that we hand them to. I don't know if does that help? Was sort of a good answer? Okay, I think we're there. I think it's the end of a long day. You are the few, the proud, the beautiful. I got to tell you, you're the most handsome, attractive people I've ever spoken to. Personally, I think you should give yourselves a round of applause. I am. Thank you very much. Okay. Yeah, my pleasure. My pleasure. I will say one last thing maybe is just that one of the things I'm most excited about, this is a better answer to your question that you asked before, well, what's exciting me? What's exciting to me is the most exciting stuff is when we can take this kind of tool, which is one way of looking at the world, and we kind of intersect it with other ways of looking at the world that get really close to the social side of work, of life, of like how communities are arranged, and how we can take not just the tools, but the ways of thinking behind the tools and bring them into communities like this one. So I just want to say on behalf of Planet, we are really excited to support and to partner and to contribute and to help sustain and do all the other things this important place, because I really do think that you're at the beginning of your journey, but it's like the problems are only going to get more interesting, more important, more salient, and frankly more tractable. Like I think we're going to have the tools to actually put a dent in the problems, not just describe them, And in the era where you can't do very much about problems, we often fetishize them. It's like who knows more about the problem is more important than who knows less about the problem, when it might be better to say who's actually having greater impact on the problem. But if that we're entering that phase of real application, and so that's really exciting. Anyway, thank you very much, everybody.